So
welcome here. Yannis Kevrekidis today from Johns Hopkins University. Yannis is the Bloomberg Distinguished Professor in the departments of Chemical and Biomolecular Engineering, Applied Mathematics and Statistics, and in the School of Medicine at Johns Hopkins. He's a member of the National Academy of Arts and Sciences, a Packard Fellow, received the Presidential Young Investigator Award.
Yeah, I used to be young, yes.
There are a lot of other honors.
And promising.
So yeah, it's really great you are here.
It's my pleasure.
And so let's get started with the seminar.
Okay, thanks. So thanks for having me. And this is not this is one of the titles that I used to like to give. No equations, no variables, no parameters, no space, and no time. It turns out I gave this to a conference, and then the plane didn't start because of there was a big snowstorm, and I didn't go. And then they put the title and said no Yannis at the bottom. So anyway. So I'm going to tell you a few things that are a bit historical for me. This is very informal, interrupt. What I want to really talk to you about is something that we did for effective free energy surfaces. And this is a slide that I like to use. I stole it from Julio Tino, who is the dean at Northwestern. And so you can think of these are simple systems. They are described by a few degrees of freedom. Billiard balls, they have a mass, they have a center, they have a coefficient of restitution, whatever. This is complicated systems. Complicated have many degrees of freedom, but every degree of freedom does a different job. And then these are complex systems, many fishes, many people, many molecules that you guys all play with. And the idea is that somehow things emerge from the interactions of these many more or less equivalent things. And he wanted to put this up because he wanted to make a contrast between complicated and complex. And I wanted to put it up because I wanted to point out that everything is complex and simplicity is in the eye of the beholder or in the eye of the modeler, because a billiard ball is a lot of molecules. And it is only because we are so used to thinking of it as a billiard ball with a mass and a center and a radius and a coefficient of restitution, and because we can write equations at the macroscopic level, that we think of it as simple. I mean, if we had to compute, I don't know, the Schrödinger for every molecule in the billiard ball before we decided if it will fall in the corner, we would never play billiards. So the system is complex. We think of it as simple because we can describe it in terms of macro observables. That would also not be useful. Not only do we describe it at macro, but we have macroscopic equations, classical mechanics and collisions, and that allow us to describe it all at the macro level. And I spent many years of my life asking kind of the following question. Look at this. This is my little toy example of a complex systems. It comes from some work of Tony Roberts, who is a mathematician and a very good friend and a really smart Australian guy. And he worked for some years on this model. So this model, these are two different views of the same thing. On the left is a whole bunch of dots. Each of these dots is a model of a microorganism, a plankton on the surface of the ocean. Good, help us. And you run them, sorry. So let me so there is the detailed model, and you run the detailed model, and what you see on the left, I paused it, is what the plankton do. And what you see on the right is the correct macro statistics to look at. It's the pair correlation function as a function of time and the radius of the neighborhood. And if I continue the movie, you will see that on the left, it is a horrific, messy, stochastic, blah thing. There is striations, they give birth, they die, but if you look at the pair correlation function, it very quickly evolved and it went to a very nice steady state. What's the point of this little stupid thing? That the same thing can be in principle described in terms of its detailed physics, or you can observe it at the macroscopic level. Here you look at the pair correlation function. If you could write an equation for the pair correlation function, and that's what you care about, there's no reason to simulate the microscopic problem. I mean, if you can write chemical kinetics in terms of concentrations, it would be stupid to do them by reactive molecular dynamics. If you can do the Navier-Stokes as a PDE for the velocity and the moment, or the momentum and the density, it would be stupid to run molecular dynamics for flow in a pipe. Okay, so it's very important, if we can, to find macroscopic descriptions, not only macroscopic variables, but also macroscopic equations. And this is a thing that I thought in 2020, along with Bill Gear. And let me explain what the deal is. We have microscopic equations for the particles. We have some reason to believe, somebody has whispered in our ear, or our friend has told us, that you could actually maybe write a macroscopic equation in terms of the pair correlation function. But you have no way of learning this equation. It would take you too long, or you're not smart enough to do it. Okay, now you want to look at what the pair correlation function will be after some time. One of the things you can do is that you can start the particles and run the particles until they get to stationary pair correlation function. The question is there a chance you can do smarter than that? And then you think, if I had an equation for the pair correlation function, I would take an initial condition in the macro space, I would go to the equation, and the equation will give me the time derivative. And with the initial condition and the time derivative, I would make an Euler step at macro scale, macro time. Yeah, but I don't have this equation to help me do this. So what do? I kind of do the best of both worlds. I use the idea that there is a macroscopic equation. I initialize the pair correlation function, and then I create particles that have this pair correlation function. This little arrow, which is very non-trivial, is called lifting. How do you create molecular configurations that have the right coarse variables? And then you just run the stupid code that you have in your pocket, but not forever, for just a short time, just long enough to be able to estimate the time derivative of the macro variables. And now that you have the time derivative of the macro variables, you take a big Euler step in macro time. Now, when you get to the new initial condition for the pair correlation function, you have no idea what the particles are. But what do you care? You initialize particles again with the right pair correlation function. You run another little bit, and you make another jump. You see, the important thing, and by all means, stop and shout and complain and whatever. If you want to look at the macro behavior, you don't really need to know where every molecule is, or where every plankton is, or where every little hydrogen is that moment. It's the macro behavior you want. Therefore, there is no reason for you to integrate in great detail all the way. It's enough to integrate just enough to get the right-hand side of the macro equation. And then you do with it exactly what you would do if you had it as a formula. Okay, so what we do is integration, but the right-hand side does not come from a formula, it comes from a brief burst of micro. We do Newton-Raphson to find steady states. Our Newton-Raphson, the residual and the action of the Jacobian, they don't come from a formula, they come from a brief burst of simulation. And so the idea is, I know that an equation exists, but I unfortunately do not know it. Okay, either I work for 10 years and learn the equation, and then I can do whatever I want with it. Or I use the microcode, and I use the idea that an equation exists to help the microcode give me just the numbers that I need that I would have gotten from the equation. So we call this equation free, not because it has no equations. It has equations at the fine level. It has no equations at the macro level. But we use the idea that these equation exists and what we would do with them if we had them as design of experiments for the microcode. We run the microcode to give us exactly the numbers that we would get from the formula if we had it. I have a funny example for this. I'll say it and then I will stop. And really, I mean, I want you to, before I go on, I would like to have a sense that you're okay with me. Let's say that I have a friend from, I don't know, so usually I had a friend from China as a visiting professor in Princeton, and they gave me a book with some of the early poetry, you know, like around maybe 500-600 AD. And so
in Chinese, I assume.
Yes. As a matter of fact, hold a moment. Here is the book. It says Poems of the Masters, Chinese Classic Anthology of the Tang and Sung Dynasty Verse. Okay. And they have the Chinese poem in every page, and then on the other side they have the English translation. So suppose that I want to impress Yusu and I want to tell her a poem in Chinese. So either I have to kind of learn Chinese, or the other thing is I have a dictionary and I only translate the words that I want. You understand? This is the idea. The idea is you can learn Chinese and then you can tell poems and recipes and whatever, or you can do just enough to do what you want to do. So this is the main idea in equation free. Use the particles to do just what you need to do to find the macro thing that you want. Do I sound like selling used cars, or do I make some sense? You see what I'm saying? Okay. Now, usually at this stage, people complain, wait a minute. It's not easy to initialize something with a given pair correlation function. Or wait a minute. How big should the time step jump be so that, so somebody wants to ask, please. Armin, you have to unmute yourself.
Here. Yes, I can unmute myself. Yes, so a correlation function usually describes a random process.
Go ahead.
Okay. Yeah, so usually describes a random process. So is there some kind of assumption of randomness in the movement of these particles? And if not, then how does the derivative of the correlation function encode the microdynamics?
Okay, there is several layers of answer. In this particular case, let me say that, okay, here's the cheap part. For this system that has a number of things that are random, there is random walk for the particles, there is random swishing by the ocean, there is all, it turns out that one can write a closed equation for the pair correlation function. I had the reference. I'm going to ask you to believe me that it is, you can, in the same way that you can get the Navier-Stokes from the Boltzmann equation, you can get an equation of the pair correlation function for this problem. You don't like this problem, you can get an equation for the density of random walkers by running random walkers. We do it in our first stochastic class. So trust me, for this problem, there exists a closed equation for the pair correlation function. Now, how does it encode the microparticles? Actually, it doesn't. Or let me rephrase it. Do you think that the diffusion equation encodes the microscopic behavior of the random walkers? It is a realization of it, but does it really encode it? Not necessarily. You could have many things that look like a diffusion equation macro, of which random walkers is but one realization. Fair? So I'm not trying to learn what the random walkers are doing. I am trying to predict or analyze the macro behavior of whatever the random walkers are doing. Fair enough? You're nodding, so okay, good. So, okay, so all of this is based on Macrosmoothness. So think of it, what we do is that we run for a short time and you come down on a slow manifold. When you look at this, you should think very much of like biased umbrella, you know, of biased samplings. Instead of starting at arbitrary initial conditions, you prepare the initial conditions, then you let them free after they are ready, and then you can estimate time derivatives of the macro quantities by the short burst of the simulation. And at the right limit for singularly perturbed problems, you can do lovely numerical analysis of this. For those of you that recognize the name of Bill Gear over here, I was very fortunate at some point in life. Exactly when I was doing this, Bill Gear retired from his job of running NEC, and he was in Princeton, and he came to a talk that I gave in applied math, and then we've worked together for 20 years since, because he didn't have anything else to do, I guess, or he liked this stuff or whatever. So you can do this with proofs and at some appropriate limit. Is this helpful, the proofs at some limit? No, but it makes good math papers. So the main point that I told you so far, you have a detailed simulator or even an experiment, and somebody tells you, you see, the biggest thing in what I kind of hid under the rug now is that I told you, hey, look at the pair correlation function. Yes, but if you look at the particles running around, how do you know that you should look at the pair correlation function, right? What is the right reaction coordinate? So for now, if somebody tells you what the right macro coordinates are, then you use the idea that the coarse equation exists to accelerate the simulation. So as I said, we call this equation free, but how the hell do you know what the right variables are? And then we go to, there's many things to go to, but our particular poison for the last 20 years is diffusion maps. No, 17. So where do coarse variables come from? This is always fun to discuss. Sometimes you have a cloud of particles. Hell, you use moments of the distribution, the first moment, the second moment, the third. At some point, you have enough moments to describe the particle well. You know, you have a function, 1 Fourier mode, 2 Fourier modes, 3 Fourier modes. At some point, you're going to have enough. And you go from a function which is infinite dimensional to 23 Fourier modes. Okay, it is a coarse description. So sometimes it comes from statistics, vanilla statistics. The second one is kind of funny because you can have a person who is very smart and understands how he figured out the right variables, or a person who is not so smart but has some sort of intuition, which means their brain does the image processing, and they can also kind of come up with the right variables. So whether you work very hard with the Boltzmann equation and get the Navier-Stokes, whether you work very hard with a protein and figure out what the right macro coordinates are, whether you, I don't know, you are a phase field person and you can find the right phase field equation, or whether you are somebody who somehow has a sixth sense about the market. You may not even know what you are observing. You may just observe if people are enthusiastic or not, or if your barber was talking about a stock or whatever. So, but I'm just trying to say that many people, look, all of us put our money in some retirement account that is given to some hedge fund because we believe that the hedge fund persons know how to predict things better than we do. Okay, maybe, hopefully they do, but maybe do they know how they know what they're predicting? Who was it? Was it Dick Cheney, right? He said known unknowns and unknown unknowns. So maybe you have somebody who has a sixth sense about something. This means the data mining was not done explicitly, but was done subliminally in their head. So sometimes there is experience. We call this experience, okay? I remember people from ExxonMobil once giving a talk, and they were saying, allow me to measure the vibrations of one of these huge riser reactors, and I will write you a controller for it. And you kind of all have a feeling that there is somebody in the physical plant of the university, and if nobody else knows what goes on, you go and ask them, what's happening here? And they've seen it before, and they kind of know how to think. This is all just a lot of words to tell you. You can be very smart or very experienced or brilliant or something and come up with good variables, or you can kind of do data mining, which is what we do because I am neither very smart nor very experienced, nor do I want to spend a lot of time to learn the tools necessary. So our way of finding good variables is diffusion maps, and we've been doing it for some time. For 150 years, people do PCA. And then I also wanted to point you out to a paper of mine from 1992 that uses autoencoders in order to find good variables. They came out in 1991 and they were called nonlinear principal components. And then since 2000 or 2002, what we do is that we use diffusion maps, which is one particular way of doing finding of parametrizing curved manifolds parsimoniously. Let me just say it's an eigenproblem, and in some way it looks like principal components in that you have a big matrix and you find its leading eigenfunction, but it's not the same. And there is a lot of theory from harmonic analysis about it. You're using a diffusion kernel, you're using random walks on the data. Not important, most of you already know. Some of you that don't know, I'm not going to tell you in detail here, but we've been using this for around 15 years for finding coarse variables for molecular problems. And so I think our first paper on this is around 2005. And now I want to tell you, okay, so somehow we found coarse variables that are decent. We should discuss it again at the end. We found coarse variables that are decent. And now I want to tell you something that I thought for the first time. The paper is 2003. It's with Bill Gear, and it is called Computing in the Past with Forward Integration. And in a paper that we had with Gerhard Humer in 2003 about alanine dipeptide, God help us, we used this. Let me tell you this, I am still, after 20 years, I'm very fond of it as an idea. Remember how I told you, if you have a system that has a separation of timescales, yes, then let me go to the annotate. So there is some fast and some slow stuff, okay, things that equilibrate quickly. So this is my slow manifold. I run and equilibrate quickly, and then I evolve on the manifold. And up to now, I told you, I estimate the time derivative and jump forward to save some time, okay? That's what I told you up to now. Well, it's a very interesting idea. Let's do exactly the same thing, run for some time to come down on the slow manifold, evolve a little bit on the slow manifold, but then not do backward Euler, do forward Euler backward in time. Take a big step backward in the dynamics. Okay, now you're going to say, wait a minute, this is a singular problem. Backward in time is not well defined, it explodes, blah. Yes, I don't integrate for many steps backward. I take the one big backward step and I integrate forward a little bit, come down to the slow manifold, estimate the time derivative, and then take another big backward step. It sounds like backward integration. We called it coarse reverse integration. What we really are doing is that we are extending backward in time the geometry of the slow manifold. Let me say this again. What we do is that we use forward simulations and then really geometry to go backward only in the slow direction, not in the directions that explode outwards in many, many ways. Of course, when we do this, we make an error, and that is why we don't continue doing it, but we integrate forward a little bit and then big back, forward a little bit and then big back, forward a little bit and then big back. So this is a way of going back, if you will forgive me the expression, in the expected backward direction. From all the directions that explode horribly backward in time, we are going back in the direction that does not explode, in the slowest backward direction. For those of you that play with mildest ascent, we are kind of mildestly ascending the potential. So give me a moment, Armin. I don't know if this is a new hand or the old hand. What we did with Gerhard is that we start close to the bottom of a well for alanine dipeptide. We run forward a little bit. We ran a bunch of short trajectories forward. We estimated the effective drift, and then we went backward. We went up the effective well. Up the effective well, not on the many crazy directions that explode backward, but the slowest, the mildest direction. What I'm telling you is mildest ascent, almost, not exactly, okay? Mildest ascent in 1993. This is important because this is what I'm going to use to get effective free energy surfaces. I'm going to start at the bottom of some well, and then I am going to go outward, backward from that well. I mean, I'm going to literally run the molecular dynamics backward, but I'm not. I'm going to effectively run the molecular dynamics backward by running them forward for a short time, estimating the local effective Langevin, if you want, and then take that further and further and further out. This is the announcement of what I'm going to tell you. But I wanted to tell you that there is a simple deterministic version of this. Yes, Armin?
I think I got a little bit lost here.
Yes.
Can you tell me again what the red line, so this manifold, what does it represent? And perhaps
Okay.
example of
So,
line
very good. Yeah, okay. So, and then maybe also Hendrik, somebody can also help me. So think of this as being a coarse variable, the x-axis, and then think of this as being all the other degrees of freedom slaved to the coarse variable. So it's all of the little vibrations of the molecule slaved to the two dihedral angles. But in general, I don't know what all of these other degrees of, if you tell me the two dihedral angles, I don't know what the other degrees of freedom are doing. So if I run for a short time the full molecular dynamics, the remaining degrees of freedom are going to statistically equilibrate with the slow variables. And if I run a little further, I am getting a sense of how the slow variables are evolving with the rest equilibrated. And now that I have a sense of how the coarse variables are evolving on the free energy surface, I know the local effective potential, I can estimate the local effective potential and go up in the local effective potential in backward effective expected time. Did I make so? Let me say this again then. I run the molecular dynamics for alanine dipeptide for some time, and then I record the local average rate of change of the two dihedral angles. And then I take a big backward step in the two dihedral angles. Run forward for a short time, estimate the time derivative of the two dihedral angles, and then make a big backward step again. Can somebody help me if I am not saying it well? I may.
Does that mean that when you run the simulation, as you describe in this green line, then does it have to be constrained by this dihedral angle variable?
No. Typically, you would. I understand that it is quite useful or usual in this world that one might do a constrained evolution. The way that I'm telling it to you now, no constraints. Forward time evolution, everything is unbiased. The only thing that I'm biasing is the initial conditions, not the dynamics in detail. It might be useful to do it constrained. There is a lot of things about initializing on a slow manifold, but let me allow me to say, no, unconstrained. The only thing that I kind of play with is the initial conditions. If you want to do it constrained, which is fair, then you could say, let me run it constrained for some time, and then let it free, and then estimate the time evolution of the coarse variables of the unbiased, but somehow prepared. Okay.
Yannis, sorry, just to follow up. So
yes.
This requires you start somehow at the bottom of the energy landscape and going backwards. So why not start from far away from the and then do forward?
You start anywhere you want. It's
but
just
why
that for what,
don't we do this, like let it converge on the slow manifold and then go forward? What is the advantage of this backward? I guess I didn't fully get.
Because going forward, why am I selling it this way? I think there is much more to gain by doing this rather than forward. Forward could be also useful, but if you are at the bottom of a well, going forward would take forever to get you out, while doing what I am doing would get you out in no time. You see, that's why I'm selling it by starting at the bottom and going backward rather than forward. If it is very slow, yes, you can do it. Okay? So I already told you, if you want, about the coarse forward integration. I'm trying to sell you the coarse backward integration, because the coarse backward would get you to escape the wells very soon. Okay. So, okay, this is old stuff, but I am saying it so that I have to stop the annotation so that I can go forward. Why is it not letting me go forward? Yes. Okay, so this is I have to erase all of this stuff. Wait. And so this is what exactly what Yusuf said. I am, come on, where are the erasers? Here are the erasers, and I kind of erase
somewhere
this.
up. Yeah, yeah. Or delete all you can use.
Yeah, this is what I'm. Oh, there is a delete all. Thank you.
There's a clear all. You can just.
Oh, there is a clear all. Thank you.
Clear
Okay.
all.
Actually, there is still one more here. Okay. So, and then I go back to, oh, come on with the annotate. Okay, so here. Okay, so this is, I got a guy at the Princeton University Press who is a graphic designer and did this for me, okay? So yes, I have an effective one-dimensional free energy surface, but it lives in a very high dimensional space and I don't know where it is, okay? So, which, think of it, this suggests that indeed somewhere there is this snaky one-dimensional effective coarse variable in the high dimensional space, and then above it there is a potential, but I don't know where it is. So what do? I start close to the bottom of some well, run for some time, I do my diffusion maps, I discover that the slow manifold is parameterized by something, and now if you think about it, so now I make a jump usually. I don't even really integrate backwards. What I do is that I go to the edge of this manifold, okay, and I geometrically extend this manifold outwards. So this is not even specifically backward integration, nor specifically forward integration. It is, if you want some poetry, it is discovering the geometry of exploration or something like that, if you want, okay? So I extend the slow manifold, and then after I extend it, then I create this as a new initial condition. Whoever asked me, was it, here I do it constrained. I run it constrained for some time, it comes down. I let it go a little bit. I take the new data. I now do streaming diffusion maps, and then I have more of the manifold, and then I extend it further. This is my flying carpet. This is a 2D free energy surface in a big domain. I have no idea where it is at the beginning. I have some initial point anywhere. I run a little bit in its neighborhood. Gee, I realize it's a 2D slow manifold. And then I do diffusion maps on this and look at these data, do data analysis. And then after I do data analysis, I have to discover where is the boundary of what I have explored. And there is, so, you know, we have Yusuf here, and alpha shapes is what we did. And after you do this, you go to the boundary, and then you use something as simple as local principal components or as complicated as geometric harmonics of whatever kind. And what you do is that you create new initial conditions. And then you bias the new initial conditions, you run again, and you do it again and again and again, and then you fathom this two-dimensional surface. So this is the main thing that I am kind of trying to sell to you. We believe there exists an effective free energy surface. It is parameterized by some coarse variables. I have the black box simulator. I do not necessarily want to, I mean, if I knew the coarse variables, I would run umbrella sampling everywhere and I would be done, okay? But I don't know what the coarse variables is. This is the thing that's interesting here. I get the initial points and I get the local geometry around those points. I bias the collection, get new points, get new samples, and now I create, I augment my geometry as it goes. You know, I explore Africa as I walk around it, if you want. Let me tell you what are the tools of the trade? You need something that simulates unbiased molecular dynamics, Monte Carlo, whatever you want. You need something that finds the boundary of what you have explored. And after you do that, you need a way to extend. You can do it with local PCA. You can do it with geometric harmonics. You can do it, we developed sign diffusion maps with no flux boundary conditions. It doesn't matter. Some way, some differential geometry. I asked Hao Tieng to make me a sketch. He made me this sketch. You do some differential geometry to extend locally the manifold. You use the extension to get new data. Okay, here is the obligatory dumb example. You do alanine dipeptide, you run it for some time close to the bottom of one of the wells, you get the blue points, you analyze the blue points, you find, come on pointer, here's the blue points, you use alpha shapes, you find the boundary, these are the red points, and then you use local PCA to extend in diffusion map space and you get the green points. Good. Now what you must do is that you must do this lifting that we discussed. You must create conformations of alanine dipeptide consistent with the coarse grained coordinates. We used to do things like biased sampling with constraints, as you said. We used Plume in the paper. We now have a code of our own that does biased sampling with diffusion map coordinates. I don't know if many people have it. Do you guys know of somebody who does umbrella sampling with diffusion map coordinates as opposed to some linear combination of stuff? If you do, tell me. Okay, so you create initial conditions, you run from those brief bursts now, not long bursts, brief bursts from the green points. You do that, you get a bigger patch on the carpet. You find again its boundary, you extend it again. You lift again to detailed simulations, run brief bursts in parallel with all of these, and it takes 2 rounds of this iteration. And yes, of course, this is a trivial example, and you can unfold the stupid little molecule. The important thing is that these macro coordinates that you see here, these Xi1, Xi2, they were not known at the beginning. At the beginning, we only knew the yellow part. We built this geometry, God help us, as we were going. Okay. Here is, okay, this is the non-trivial example. Is there something that maybe I should clarify on the trivial example? Yes, you should.
Yannis, so the lifting, I mean, how do you define that in general? That's a hard map to define, no?
Oh, the lifting is whatever my initial data were. Is that what you're, the yellow?
The lifting operator.
Oh, the lifting, sorry, I heard the left thing,
no,
which is not what you said. Yes, lifting is a matter, okay. Lifting is the biggest mess in everything we all do. What do I mean? You see people doing all kinds of operations in latent space, but then you have to reinitialize in full space. How the hell are you going to reinitialize in full space? Okay, so you know, okay, so an easy thing to do, what everybody does up to now, right, is to do biased sampling. As a matter of fact, I'm writing a stupid little paper, which maybe is really stupid to write, that says, hey, you guys, all of you that do guns, we always had ways. I mean, a gun is a way to lift. Are you okay, Yusu, with this?
Yeah, you can, right.
Okay.
You can
so
create.
What I'm saying is people were doing lifting a long time with reasonable tools, like initializing on a slow manifold, like, you know, biased sampling. But okay, so on the one hand, I'm saying it's very difficult. On the other hand, I'm saying it's easy. We were always doing it. What's the problem? The problem is that for some things, doing bias sampling is easy. But if you go back to my stupid example at the beginning where I said initialize with a prescribed pair correlation function, God help you, okay? It's not at all easy with a prescribed pair correlation function. Sal Torquato in Princeton has written, I don't know, 10 papers about initializing with the right pair correlation function. And the trouble is not that. The biggest trouble is in precisely what, let's say, Hendrik is. If you want to design molecules, there is discrete chemistry, right? And everything that I'm saying here is based on manifolds. And so how you're going to do lifting when you have to decide between a carbon and an oxygen, you know, God help us. Same thing when you want to initialize graphs. You may know the statistics of graphs. So you're right, Yusu. This is one of the biggest problems in the world, in my mind. You operate in the latent space, and then you have to go back. If it's a manifold, you do geometric harmonics. You do whatever you want. If it's not a manifold and a discrete problem, God help us, there is nothing systematic, and now all the smartness goes there. I'm very interested in what you think.
I had a question on the same topic, Yannis.
Yes.
Which is the mapping from full space to reduced space by its nature is many to one. That means the inverse map is not unique, that there may be multiple lifts.
Yeah, and
this can influence, so how you lift can influence what you get, because there's many answers. How do you deal with that?
Yes, thank you, you're right. So there, I'm going to have a very cheap answer, and I am interested in your reaction. If the problem can be described by a slow variable, then the effect of the other variables over the times of interest for you is forgotten. There is a point in what I'm telling you. Here is the point. I am not evaluating things with the lifted problem. Did you notice? Let me, you see, how to say, I have to be honest where I am dishonest. Remember, do you see this little plot down here? Do you see this yellow thing? This yellow thing says, I don't use the lifted thing as it comes. I let it run a little bit first. Do you see what I'm saying, Leo? I mean, I don't know to what extent you buy it, but the important thing is that if the problem is describable in terms of coarse variables, then this is an attracting manifold.
I see.
And therefore, so this is my saving grace. I have the simulation in my pocket, and I have assumed that the simulation will heal such errors.
I see.
We can talk for a very long time, but that's the idea. Fair? Okay.
Okay.
No, it's
Thank
true.
you.
If I use the lifted as is, I would be dead. I don't. I heal it by the physics in my pocket. Okay. Okay. So yes.
Got a question too.
Yes, please.
Go back to the Plankton example for a moment. Do the coarse variables reconstruct or recover the 2-point correlation function?
In the original problem, I didn't tell you what I did to lift. In the previous problem, the entire pair correlation function was the coarse variable, and the particles were the particles were the fine description.
But the idea is that you don't know ahead of time what these coarse variables are going to be.
That's precisely why I said in this problem, I did not tell you how I knew, and I knew it because Tony Roberts told me, but how do we go about it today? We do. So here I'm talking about discovering them on the fly as opposed to knowing them. I used that problem to tell you that everything I do depended on knowing in advance the coarse variable. And how do we know them? We get them with data mining on the fly.
So I'm still confused then, because if you try to learn these variables for this procedure, you know that you're getting variables that represent the system, but you don't know what they are. So how can you infer from there and do lift?
You're asking about interpretability. Okay. So the first question, you're right, thank you. Ask it also in the end. Do you care? As long as you get the right result in the end, what is the effect, what is the transition state, and what is the escape probability, and do you care if you know in what variable I did the calculation? Let me rephrase, I'm being facetious. If somebody had a logarithm table and you asked them to multiply two huge numbers, and he made them logarithms, and then he added them, and then he told you the answer. If the answer is correct, do you care if you did it with logarithms or with some other transform? I'm being facetious, but you understand. So, yeah. But interpretability is a big thing, and I can tell you what we do. What we do is we take the variables, and then here is our version of interpretability. Marina Meila has another one, which is kind of comparable. Then you go to a domain scientist, and you ask the domain scientist, oh, domain scientist, I have found that 3 things are important in your problem. Can you suggest to me 3 physical things that you think might be relevant? And they give you a various triplets of physical things. And then you go and check that the Jacobian of the transformation from yours to the physical things is 1-to-1. And among all those that are 1-to-1, the one that is the better is the better by Lipschitz. And then you say, you know what? The 3 things that you told me are 1-to-1 with the ones that I got. Okay? Having said this, allow me to say another thing that I like. I will not find it now, but I have a beautiful paper that I hope I will steal its title. It is a paper that was done in the financial industry in the late 1990s, and it is called Reconcilable Differences. And the whole point is they had 3 different models of the market based on very different observations. They had different optimization functions, and all the buy and sell decisions were the same. It really does not matter.
No, I understand,
yeah.
But it seems to me that then if you get some variables and you don't know what they mean, fine. But then to the lifting, you have to do it by some form of machine learning, I guess. That's the only way.
No, okay. Okay. Remember, so the thing that is important for me is that my lifting is done because I have in my pocket the original detailed code. If I have in my pocket the original detailed code, I may not know what my stupid variables are, but I can do umbrella sampling with them. So I am not putting configurations out of a hat. I am using the coarse variables to guide me where to search, and I use the actual code to do something afterwards. Is this, you're nodding, so I hope you're okay with me, at least for the moment, yes?
Okay, I understand.
If I didn't have the code, I wouldn't the hell know, okay? There could be, I mean, think of a singularly perturbed problem. There is a whole bunch of values of the fast variable that correspond to the same slow variable. They are extremely improbable. I wouldn't know which one to pick. It's having the dynamics that help me pick decent ones, probable ones.
And maybe doing some sampling within that space.
Well, this is again, it depends on how you do the sampling. If the sampling is enhanced by some physics, if you do some metropolis with a good energy, then you could do some. But even then, I prefer not to go there. I prefer to say that I use the physics to help me do the sampling dynamically. I appreciate you could use the physics to help you do some Monte Carlo sampling that is not dynamic. I don't know, humor me, I'm a dynamics person. I always think I have a dynamic code to run. Yeah. Is that okay? But you're right, yes, it could be some, I mean, after all, what does the dynamics do? It samples things based on the dynamics. Okay, so this is not, okay, this is my work with Gerhard, okay? So he was looking at MGA2, which is a pretty big thing, and it has something to do with deciding whether, you know, whether yeast makes more unsaturated or saturated fat. So given that he's in Frankfurt, this is important for bread, it's important for beer, it's important for all kinds of things. And Gerhard had this long Martini simulation along with Roberto Covino, the postdoc. This does look very good, but basically they had, I don't know, they said 6 months of kind of running this dimer, and the conformation of this dimer would tell you if you make more saturated or unsaturated fats. Why? It's their work. I could give you an explanation, they would give you a much better. So you run all of this, and then you do diffusion maps, and this is what it looks like, this world for this dimer, which is a part of the protein. And the point is, do I have to run for that time? No, so I zoom in, I sit at one of these places, I pick one configuration at random. The phenylalanines are just to give you a feeling, because as it just looks all like strings. And then you take this initial condition and you run a little bit at the bottom of the well. So you see, usually this is at the bottom of the well. And then you get these guys, and you get these guys, and you think of these guys as the shell of, you know, of a Russian doll. You take the shell and then you extend the manifold outwards, and you get the green guys. Are the green guys visible? Okay, and then you run a little bit from the green guys, and some of them fall back in, and some of them go to some part of the well that there is no exit to the outside world, and some of them go to some other well. Okay, this is just to make the point. You make intelligent extensions of your exploration, and then you explore from there. Okay. For those of you that have heard Cecilia's paper about diffusion maps, molecular dynamics, Cecilia finds their boundary and starts at the boundary. We are saying, if you found the boundary, start farther out, in particular, start higher up in effective free energy, it makes much more sense. I mean, that's the point. Explore, take advantage of the geometry that you have found. So what is it that we did? This very grainy and shitty colored picture was our triumph. This is the world for the dimer. The brown part, all of it, is what you get from the 6 months. The blue is what you get from, I don't know, a couple of days. Sorry, the words that I'm saying are not really appropriate. So you do it, but if you continued, it would take 1 month to escape from the first blue. But if you take the first blue and you find the boundary of the first blue and extend the manifold and do another round and another round and another round, within 3 of these rounds, with lots of parallel bursts from many points now, not just one, you can basically fathom the world. And the reason that Gerhard was very happy, and I was very happy, is that already from the second expansion, and very clearly at the third, you find the dissociation of the dimer that had never happened normally. Okay, so this is geometry of exploration. This is basically what I wanted to sell to you. And now this is my entertainment part. If you have not heard me talk about this, you will, I hope, like it. I want to share my sound. Where is the sharing the sound? Can somebody help me?
Oh, somewhere in the upper part, I think you can find a menu when you screen share. You know, it says share sound under options or something.
Okay, let me stop sharing for a moment. Please forgive me in case it, or maybe it's in the more share sound. Ah, yes. Okay.
Yeah, something like that.
I am very happy. My screen sharing is paused. So what do? Okay. So I like this one very, very much. I hope you will. So this, can you hear me? So here is Indiana Jones in one potential well, and he has to go to the other potential. There's no idea how to go from one well to the other. And Sean Connery, his father, is going to die if you don't go quickly to the other potential well. And his father says, I mean, he doesn't know what to do. And says, you got to have faith. What is the faith? The faith is there exists a low dimensional free energy structure. So he puts his hand on his heart. And then he goes out straight. Okay. Okay, look. I don't know if you remember the movie with your kids or by yourself, the young people. Yeah, and you see, he does not fall because he happened to, he doesn't see the path, but there is.
Are we supposed to see anything, Yannis? I think I only see the blend slide.
Yeah, right now we have a white screen. Maybe
hold on a moment.
We only have the slide with leap of faith. We don't see any.
God help me.
I assume you're showing Indiana Jones.
I am showing clips. Indiana Jones. Please forgive me. Oh,
yes.
you should have stopped me earlier. But it is so good that I hope you will forgive me about this. Let me run it, and then please tell me. So there you go, and then we go. Why does it do this? Hold a moment. I want to share. Okay, let me maybe stop sharing and then share again. Share. And now I want to go.
Now I think go. Yeah.
Hold a moment. Let me. It says PowerPoint not responding. Then this is the thing I wanted you to enjoy. Bear with me. So if you remember then the Indiana Jones business, which I hope you will now maybe get. Okay, so.
When they leap from the lion's head,
Indiana Jones?
they prove his worth.
Yes. Are you guys seeing it? Okay.
Nobody can jump this.
So this is the other potential well. And as I said, his father is going to die.
And you must hurry.
The other well.
Come quickly.
And he doesn't know how to go. This story will have a funny level.
It's a leap of faith.
He's supposed to have.
You must believe, boy.
He has no idea where
you must believe.
He puts his hand on his heart. He goes blind. If he can go in the right direction, what he thinks. And please look, he's lucky. And he puts up his leg. And what he does is that he doesn't fall. Why is it that he doesn't fall? See where the bridge is. And now this is my allegory for Parinello. Parinello is, this is what we do. We throw a little sand on the bridge to know where to go. and Parinello fills the whole bloody ravine with sand so that he can walk on it on the other side. So I think we're better. Okay. Now, this is what I wanted to briefly tell you on this stuff. And now, depending on your disposition or appetite, there is a couple of other nice things that I want to say, but maybe we can stop here and discuss. You can kind of see the many things that are interesting for me here. I mean, with Hendrik, we've said, let us try and do this not for folding MD, but for a reaction, for a reactive process. With Yusuf, we've talked a lot, and I hope we'll kind of reboot on looking at what's the best way to extend the geometry. There is all kinds of, I would love to also be able to talk with Leo about a number of these things and, you know, learning functions on these manifolds. And if somebody has some good thoughts about lifting in discrete problems, even if it's empirical, I would really, really like to know. But the basic idea in everything that I told you is a simple one. If I look, even if you have a wonderful model, when you go to the computer, you never look at the model. You say, what is the velocity here? What is the force there? It is hiding in the subroutine, and you just once in a while answer questions and get answers to tell you where to go next. Every algorithm we use, every iterated algorithm we use, is really a protocol where to do the next function evaluation. What I'm basically telling you is that whether in the subroutine lives a beautiful, compact, closed form model, or whether in the subroutine is somebody who calls the microsolver briefly and gets the same answer. And ultimately, if in the subroutine is somebody who calls the lab of your friend that can do this experiment and tell you the number, to the algorithm, it makes no difference if the code in the subroutine is explicit, if the code in the subroutine is microscopic, or if the code in the subroutine is a little experiment on the fly. The algorithm for how to explore remains the same. And that's the thing that I felt 20 years ago is exciting, and I still think it is. Okay. If I oversimplified, you understand always the devil is in the details. So what we did with Gerhard is that as we walked, we had to change, like we used local principal components every time. And then after we collected the data, we threw it back in. We didn't do it streaming. If one of you has experience on doing streaming very nicely for diffusion maps, I'm interested so that I don't do it from scratch myself. You know that, I mean, you can augment the kernels and follow things much faster than redoing the diffusion maps again and again in batches. There is lots of interesting things to do. Okay, I am going to look at who says something in chat, but please stop me or ask me or whatever.
Thank you so much.
Yeah, somebody says they have to go. Thank you. Yeah, sorry. If you would bear with me, I would like to tell you one thing for 5 minutes, which is what we are excited very much now about, but only if Hendrik tells me to do it.
Yeah, I think we could. That would be great. Maybe,
Okay.
yeah, just give a second. Yannis, thank you so much.
There's